No, we have finished our first meeting at this point. Do you see this presentation, I hope?
Yes.
Yes.
Okay. So we go on with this subject. As I said at the first meeting, I will prepare the final version of my presentation. I put it on this Microsoft Teams platform where the files, there is a special place called files, and I put my presentation there, hoping that it will be used only during this lecture, not to spread all over the world, let's say. Okay, so we start from current slide. Next. During exercises, we have already started with a different kind of presentation of model of the system. There were normal and, as usual, linear models. But anyway, this kind of presentation can be used for different kind of objects, of models. I mean, also unlinear. So, first of all, we have so-called technical description, domain-specific description, and so on. But we are interested in mathematical description, in mathematical model, because we all what we can do, we have to our disposal the mathematical model, because when we calculate something, anyway, we have a formula for this calculation. This formula is, of course, mathematical model. So, mathematical model is the first step of systems theory attempt to any problem. For every domain, we start with building models. Models are everywhere and are used everywhere. I think you are familiar with this fact, because when you find any formula, this formula is some kind of model of something, of device, of phenomena, physical, biological behavior of human, and so on and so on. So this formal mathematical description is mathematical model. But sometimes it is useful to have for our vision block diagram, because this presentation, let's say, is very sometimes it's easier to operate on the block diagram than on the mathematical formula, I mean model, because seeing such block diagram, we can imagine the influence of the signal, influence of energy, influence and flow of money, energy, and so on. So block diagram is also very useful. And in general, mathematical model could be in the form of relation, some formulas, but we will deal here only with such models in which we can stress, find, named, so-called input values, variables, and so-called output values, variables. Because we will deal here in formal model in which we have some cause and some effect. This model are so-called input-output models. So it means that input, which we apply to the object, change the situation in this object, and the object react for this input, and we can observe this reaction in the form of output. Of course, there are plenty different models. These models are typical for probabilistic attempt in which we can build correlation models. For example, in biology, we can build plenty of models in which we connect two values, two variables, but we cannot even say what is the cause and what is the effect. For example, for sure, between the weight and height of the human is some kind of relation, and we can build a model in which on the x this x axis we will have, for example, weight, and on this axis we will have height of student, and of course there is some kind of dependency, some kind of relation, some kind of, in fact, correlation, and we can just build such a model. But in this model, we cannot say that the weight is the cause of height of the people, and ja nie wiem, czy dobrze mówię, wzrost to jest wysokość? A jak jest height, wzrost?
Height to wzrost.
Jak?
Height to wzrost.
To wzrost, ale growth to też wzrost czegoś.
A no, rozumiem, właśnie. A to chodzi o wzrost i wagę. So it means there's no doubt there exists some relation, in fact correlation between height and weight, but we cannot say that one of them is cause, the second one is reaction, and in opposite way. So with such model, you can maybe you can maybe have already met such model in probabilistic attempt, in probabilistic in lecture of probability, of probabilistic. Mieliście już, czy nie? Have you had a lecture about rachunek prawdopodobieństwa i statystyka, jak jest skala? Proszę?
Yes, we had it.
Okay, so and for example, when we try to build so-called regression models, these models are of correlation type. Of course, for such phenomena, we can also for let's say for phenomena input-output, we can also use correlations model. But in other way, when there is no strict dependency that some value is cause, some value is reaction, we can also build this correlation model and input-output model. So, going next, it means during this lecture we will deal only with such models in which we can name some value and treat them as input, as a cause, and the other values will be treated as a reaction, because we are here oriented in the direction of control of systems. In control of systems, we need to have such values on which we can have influence, which we can manipulate, which we can change in order to achieve the reaction, desired reaction. So, in such sense, we deal with input-output models. Of course, trying to describe some part of reality, some device, we should first choose the input and output values. Generally, we can choose these values freely, but of course, as input values, we can choose such values which we can change, which we can manipulate, because the final goal is to control this system. It means that we, after all these systems theory attempt and procedures, we try to find control algorithms. In control algorithms, we have such data, then we observe the output of the system, the state of the system, and we try to calculate such values which we can input to the system in order to achieve the goal, the goal we need. So that is why our models will be in the form of action-reaction, cause-effect, forcing-response. Okay, momento. Observing system, we can also distinguish so-called value noises, disturbances, which now I left these values. So we will describe, let's say, pure system in which there is no any noise, any disturbance, in which we have only input as our input values which we have chosen. We apply these input values and we observe what is changing in the object, in the system, and these changes we can observe in the form of output values. Of course, we will do it not on a real system, but on its model. That's the main idea, to work with this model. So, when we try to model any system, first we must think over what is the purpose of this model, what for we try to build this model. Then, consequently, we choose the input and output values, variables. And as I said, the choice of input is rather obvious, because as the input variables values, we have to select such values on which we can have influence later on, which we can manipulate, which we can change according to some idea. But the output variables can be chosen in different way, depending on the goal of the system, of the real system. I will show it in a minute. Next, we think what should be the category of this model and its structure. So there are different categories of model, and we must decide which one we will use. Next, it is identification procedure. I'm not sure if here should be I instead of Y. Moment. I check it. Next or no next. I mean, if it is necessary, we must use so-called identification methods, procedures, algorithms. It is depending on the knowledge which we have. When the knowledge is complete, we can just derive our model analytically, and we do not need any identification. But if not, we need identification first to build a model. Of course, later on explanation. Next, after modeling, in this modeling procedure, we have algorithms for this modeling. We have final formulas, and we try to verify our models, usually by comparing a result of calculation with the result of observation of real system, and at the end we have the model which we use, and we will calculate everything for this real system on its model. When the model will be good, then our result also will be good. Okay, and as introduction, let me present this electrical circuit. I think you are familiar with such simple electrical circuit for current, for direct current. And we have two sources of energy with voltage E1 and E2. We have three branches, one first, second, and the third one, with resistors corresponding R1 to R3. And we would like to problem. And it is normal task from electrotechnic. In electrotechnic, the normal problem is having voltages which cause the current. Try to calculate the current in every branch. And from systems theory point of view, it is a little bit different, because, for example, I can imagine that I have aquarium for fishes at home. Aquarium, maybe.
Yes.
No. Container with water for fishing. Caribbean fish is small, and I can then feed them and observe and passing my time just observing flowing fishes, colored gold and so on. And my problem is that this water needs to be heated, because we must heat this water, and not our fish will die and will be catastrophe. So let us imagine that this R3 is a heater. Heater is some kind of heater which we put to the water to grzałka, maybe heater, something to heat the water. When we put in old times or during vacation, we have I don't know, I call it now heater, as a little electrical equipment which we can put in the glass of water and then put to and give the supply to this heater, and we heat the water to boil the water, and we prepare coffee or tea or something like this. And of course, in every aquarium there is such heater which is needed to keep the temperature of this water on certain level which is desired for particular types of fish. Wanting to be sure that everything will be fine, I will apply two sources of energy, because when one of them is cached, then the second one will anyway supply my aquarium, and I have time to repair the first one. So the problem is that I would like, of course, having this resistor R3 in this branch, the current I3 is flowing. Of course, the amount of heat is proportional to this resistor R3, and it is not proportional to current, but to current I3 square. But anyway, changing voltage E1 and E2, as effect, I change the current I3, and consequently, as the effect, I change the amount of heat which I give to the water, and consequently, I change the temperature. So, wanting to control this temperature, I must properly choose the value E1 and E2 in order to have proper current, and so on and so on. So, when I would like to control later on the temperature in my aquarium, I will need such model in which the current I3 will be depending as E1 and E2. So, as you can see in this simple example, the choice of input values is rather obvious, because E1 and E2 should be these values. Why? It is clear, because we can change them. We can change and have influence for this value which we want to model, in fact, to change, to obtain desired values, and so on. So, in this sense, we can try to build a model, because we have formal description of our system. In the first task, I assume that there is only one source of energy. It means that E2 is equal to 0. And having in mind Kirchhoff's law, I can write these three equations, as you can see on this slide. And my goal is to find the dependency, how the current I3 is depending on the voltage E1. So it means in this particular task, E1 is single input and I3 is single output. After simple calculation, excuse me. After simple calculation, we obtain such formula, in fact, mathematical model of this dependency, in which on the left side we have current I3 and on the left side we have certain coefficient. Widzicie tą myszkę, czy nie? Halo?
Tak, tak, tak.
Yes.
Okay, so in this as an effect we have a model in which is output I3, and it is linear model in fact because this coefficient which can be calculated having values of these three resistors is in fact coefficient, and then we have input value E1. So it is linear model. Why? Because we have started with formal description which is linear. As an effect, of course, the model is linear. It is methodology of finding mathematical model in the analytical way. So we have in our disposal precise 100% good description of our situation, of our system, and from this description we derive desired model. For example, this one. Here we do not need any identification because we have full knowledge about our system. And this model, of course, is the best one because this model in 100% explain the behavior of this system. The next task in this situation will be a little bit more complicated because now we take into account that there exist two sources of energy, this E1 and that E2. So repeating this procedure, of course the starting formulation of the problem is the same, almost the same, because here is E2 not instead of 0. But now we search for the relation formula in which this current is depending on two values. So this model will have two inputs and one output. Of course, after simple calculation, we also obtain linear model in which this output value is linear combination of input values. Linear combination means that there is coefficient certain multiplied by this value and plus minus another coefficient multiplied by another input value. The third task is such that we change the role of the system. For example, this diagram. For example, we would like to supply certain transistor elements, and we will need for transistor certain voltages. This voltages will set the nominal, the point of work of this transistor, which is needed to have transistor working good. I mean that every transistor, every of milliards, billions, and so on transistor, need first current, direct current supply to set punkt pracy, to set punkt of work of this transistor. Having set this point, Now, next we can apply our signal, which we will transfer via this transistor and change, amplify, and so on. These signals will be for example, alternating current like sinusoid, but this signal will be amplified by transistor which have set nominal point by direct current. Zrozumieliście Państwo coś? Hey, have you understood?
Can you say that again, please?
Okay. Moment, maybe for engineer is moment.
I think you are looking for the word bias, biasing the transistor.
No. Oh, maybe. Moment, I try to activate whiteboard. Maybe we can do it. Sometimes it's working, this Microsoft whiteboard, and sometimes not. Maybe today is day without whiteboard. Maybe. Okay. It's opening in so okay. Oh. For example, transistor is nonlinear element and have different description which are given for certain values. There are families of curves for base current, particular base current, for example, voltage between collector and emitter, and here is other value. It's not the point, but the point is, it is characteristic of this transistor, and we need first supply energy to this transistor and set point in which this transistor will be working later on. So we need direct current to set this point. So when we put such voltage, we are in this point of this characteristic. And next is coming signal, which we would like to przetwarzać. Process by this transistor, thank you. And this signal, of course, is going along this characteristic, along this particular point. This point must be chosen properly in order to avoid this non-linear part of this characteristic. And after this processing, we have such signal which is going to the system and is processed later. You understand? But first we need this point of work, nominal point, which is set by direct current. So, as I said, for example, in our problem, widzicie teraz do you see this presentation now?
Yes.
Oh, and for example, this moment, this voltage and this voltage are used to supply certain transistor. So Also, we want to be sure that everything will go fine. We have two sources of energy, and we need to formulate to have under control the values of this and this current, because consequently when we change and model this value, of course this value of voltage which is put to other circuit is also modeled. So in this situation, it is just hypothetical, because I would like to explain why for the same physical, let's see, object system, we apply a different model, because it's depending on the aim of this system. And now we can consider the third task, in which we have two currents. As we would like to change these two currents, to have influence on these two currents, later on consequently on voltages. So we have voltages E1 and E2 to our disposal, and we have model change the current I1 and I2. So as effect, we need now in our model to find two relation of this type you can see. So it is problem from linear algebra. Let me remind you Kramer method for solving such set of linear equation, in which we would like to find values x1 and x2, knowing these values z1 and z2. Of course, these coefficients b are known. It is the result is, as you can see, we have here a determinant of this matrix of the system of this main matrix of this system, and it is its determinant. And in a nominator we have also determinant, but we substitute certain column of this basic matrix by the left side column vector, but corresponding to position of index of value we would like to calculate. It is obvious, and we will use this methodology, I mean Kramer attempt to this problem in modeling during exercises, and I show you later on how to do it here. So, okay, and of course applying this procedure, Kramer procedure, we obtain a result as you can see. Also, this solution is linear, because now I1 is a linear combination of two values, of two input values, E1 and E2, and of course here the same. Why? Because we started from linear description. As an effect, we can only obtain linear model with linear solutions. And now we will change our physical values into values, standard values of system theory. I mean, from this moment on, we will use not any voltages, currents, money, pressure, height, weight, force, power. No. Now we will use only standard values, which we call input value or values and output value or values. And for this first task, we can see that we deal with simple model in which we have one input and one output. And of course, writing such like this, we are not sure if our model is linear or not, because here we see function. But we will deal only with linear models, in which here we will see only coefficient a, small a. For second task, the result is that we have model in which we have two input values and one output value. And of course, this model have two coefficients, a1 and a2. Generally, this model can be linear, non-linear, but of course, we will deal only with linear models. And the third one is a model in which we have two inputs and two outputs. And description is as follows. Typical description for linear algebra. And when we see here big letter, capital letter A, we are sure that this model is linear. Moreover, the matrix describes the parameters of this model. Of course, seeing these two values and these two values, these two arrows here and here, we know that this model has two inputs and two outputs. Sometimes we can find description in which here we will see only one arrow, and notation U. Here we will see this capital A, it means matrix, and here we will see also one arrow Y. Seeing such description, we are not sure the dimensionality of our system, because matrix not necessarily be square. It's depending if the number of inputs and outputs is the same. If not, the matrix A is not square. It is obvious. So when we see here only one arrow and here also and matrix A, then information is that this object system is linear, but the number of inputs and outputs so far is unknown. And you can see here some explanation that the systems theory means that we are not oriented on any particular area. We just work on mathematical model in standard form, and we can calculate different things and then try to apply it to particular domain. For example, in electrical engineering, we can substitute the Ohm relation with the model that certain Y is a linear model of a certain U. And the second one is for mechanical engineering. And have you any comments to this? Are you there? Are you sleeping or what?
We're there, but I don't have any comments.
No comments for this B? Maybe jednak. Maybe any comment for this B point?
I have one question.
Yes.
Isn't this Leonardo da Vinci?
Yes. Yes, yes. It's not Isaac Newton, of course, but it's some kind of joke which which shows if you are, let's say, listening and watching this lesson or not. Yes, yes. It's of course it's Leonardo da Vinci, very famous from Florence, from jak on jest jeszcze, Venice and Florence, the city, very close to his name, and his grave is in Florence. I know, I read that. So, but in Venice there is two museums of his inventions, and he telling about his work and his ideas and so on. So it's very interesting. Of course, if it would be possible, go there. You will not regret. Okay. Okay. In the Venice, there is in this museum, just a little break, there is certain draw of man on the circle. I cannot this particular name. Maybe it's a well-known picture drawn by Leonardo da Vinci, in which a man is spread into some circle. You know this picture, this draw?
Yes.
Yes, and the original work is in this museum. It is forbidden to make a photo of it. Even if you made a photo, you must cancel, because there are, let's say, staff who is going around and observe tourists, and if you make some photo, then they very quickly approach to you and ask to delete this photo. Why? I don't know. For sure, we will not copy Sir Leonardo. Okay. As I said, we can apply systems theory to different branch of interest. Technique, science, economy, biology, medicine. In fact, everywhere where we try to calculate something, for calculation we need formula. In fact, these formulas are certain models of some phenomena, of some relation, of some device, or whatever. So when we calculate something according to any formula, it means that we in fact use some mathematical model of something, because the formula is in fact model. The model could be very good, could be only serve as calculation approximation of behavior of this phenomena, but anyway, it is a model. For example, every law of physics former were models, hypotheses. When we check this hypothesis very well, and we came to the conclusion that this description, this model is very well, it explains in 100% our phenomena, then this formula is classified as a law of physics, of biology, and so on. You understand this? The book of science is the book of models. It means the law of science, of physics, which before they are built, they were hypotheses, models, and so on. You understand this?
Yes.
It's very, very funny because we use models and we are not, let's say, we don't know that we, in fact, we use model and we are serious to use certain formula. Oh, it is just like according to this formula, but it was the model formula before we obtain it to our disposal. Okay. Okay. And model categories you can see on this slide. Probabilistic, deterministic. Here we will deal only with deterministic model. It means that our data are repeatable. It means that if we put some value to the system, some input value to the system, we obtain always the same reaction. Always the same, because this model is deterministic. In the real world, it's not so easy, because normally there exist dependencies, noises, disturbances, which change this output. So even if we put the same input value to the system, we observe little bit different values of output. Why? Because the noise also has influence of this output. In fact, the output is we can imagine a function of two values, of this input value and this noise value. Maybe if we would have such much more complicated model, we could calculate in 100% the reaction. But we haven't such model. The model can be very simple as one element model, to much more complicated one, in which we have connection of plenty of objects which create together the structure of the system, and this system works as one structure which consists of plenty of elements. Every model can be one-dimensional or multi-dimensional. I mean, every model can have one input, one output, or the number of inputs and outputs is bigger than one, so we deal with multi-dimensional object. As I said, we deal with linear or non-linear models. In linear model, the output is a linear combination of the input values. In non-linear, there exists certain function which describe connection relation between output and input. Of course, the linear model are relatively easy to handle, because we have linear algebra, we have matrix, we have inverse matrix method, and so on and so on. For nonlinear case, it is quite different to say something in general, because it's depending on the kind of this non-linearity. And in fact, non-linear problems are solved using using mathematical procedures, some kind of recurrent algorithms which try to achieve the solution with step by step. These methods are called numerical method of finding solutions. And the system can be static or dynamic. Static means that the changes as a reaction of changes of input, the changes of output are straightforward, I mean immediately. So it is like in direct current circuit. It means that if we change the voltage of supply, immediately in the same moment the current is changing. So such systems are static, in which the reaction is straightforward. The reaction is even in the same moment observed as the change of input. But in general, the world is built of dynamic systems, object, elements, reality. It means that if we change the input value, we can observe the output value, the change of output value in the time. For example, according with this heater and a glass of water, when we start supply this heater, the temperature of this water in this glass is changing from the temperature of room temperature to the boiling temperature. But this change takes time. It is not immediately. Even we put higher voltage, then the time will be not longer, but opposite, shorter. Thank you. Shorter. But anyway, the time, there is no possibility that this time will be zero. Even if we accelerate with a car, it takes time. Rocket, it takes time. Of course, the time is shorter than for the car, Formula 1 car, and so on and so on. But there is no zero time. It is impossible, because we cannot change our position in zero time. It requires the time. So that is why, of course, there's other so-called delay is also property of dynamic, but leave it. Now we will deal only with such static system, or with system in which we can assume that the reaction time in comparison in time of observation is so short that we can assume that the changes are immediately. You understand? Because anyway, we have model. We can, in modeling, it is normal that we assume some simplification. We omit some influence of certain values. We try to obtain as simple model as it is possible, because on simple model we will do simple calculation. Having a much more complicated model, our calculation will be, as an effect, of course, complicated. So in modeling, it is also one thing taken into account. We try to simplify the problem we try to not to take into account all influences for the output in order to explain, let's say, 90% of behavior of the system. It's enough for engineering purposes. So, for having this division of categories, of model categories, we can say that the model we have observed so far was deterministic, one model element, static, linear, and one or multi-dimensional. I hope I explained it. So we can go on. We can go on. Statistical models are typical for population model, in which for certain population we try to model something in average sense. So it means that our model will be good in average sense. Once again, it means that for particular, let's say, for particular man, the result obtained by this model and in fact in this particular man will be a little bit different. But if we take into account the result obtained from model and average value of physical measured result for 10 persons, let's say, the difference will be very small. Have you understood? I mean, the model in average sense means that the model is good in general, but for particular, let's say we have the model between blood pressure and some drug, which is taken by patient to obniżyć,
Decrease.
To decrease, thank you, to decrease this blood pressure. And we have model of influence of this of dose of this treatment, and here we have blood pressure for patient. And let's assume that is some relation. This relation is a model. And according to this model, let's say doctor choose the dose for this particular patient. But the model is obtained in average sense. We have investigate plenty of patients after giving some dose of this medicament, and we next calculate average value for this patient which obtained this particular dose. As an average value, we obtain point of this model, and we do for whole range of this this medicament which can be given to patient. And after then, we obtain model. But this model is good in average sense. It means for particular patient, there can be differences between his reaction and the reaction calculated with this model. You understand?
Yes.
Okay, so it means in average sense. In statistical, we normally deal with models which are good in average sense, because the phenomena is not repeatable, so we can do also in this sense our consideration. Dimensionality is obvious. 2 inputs, 2 outputs, and so on and so on. We call this particular problems as SISO and MIMO. SISO means single input, single output. MIMO means multi-input, multi-output. Właśnie multi-input, multi-output. We deal with this word. Co wy teraz macie? Jaki macie internet teraz? Taki, co to jest taki najnowszy? Kto przypomni mi?
Fiber optic internet światłowodowy.
Nie, ja myślę
5G.
5G?
To ja myślę to Wi-Fi takie, co to jest teraz takie, że to, jak się nazywa to Wi-Fi najnowsze? Wyleciało mi.
MIMO?
Jak?
MIMO?
No MIMO, ale okej, ale właśnie w tym nowym internecie Wi-Fi, który jakby jest, tak, szerokopasmowy. O, jak się to nazywa ta technologia szerokopasmowa?
Broadband?
Jak? Po polsku powiedzcie, to się zmęczę. No taka technologia szerokopasmowa, taka reklamowana rok temu czy półtora, no. O Jezu, no. Używacie.
Maybe it's about 5G or...
Nie 5G, nie 5G. No.
Ultra wideband?
Jak?
Ultra wideband? Wi-Fi? I don't know.
No. There is special kind of technology in which, in fact, we have MIMO technology, plenty of antenna for sending and for receiving, because in this way we can accelerate the speed of internet, of flow of the information between sender and receiver. Anyway, sobie przypomnę to jutro powiem, znaczy za tydzień czy za dwa. Okay, next we are going on. Sorry for my Polish, because it is rather difficult to explain. Jak to się nazywa? Szerokopasmowy internet, no. Nikt nie wie, po co to szerokie pasmo jest, no bo poza tym, że jak jest szerokie, to jest lepsze. Ale okej. It is obvious, single input i tak dalej, single output, multi-input, multi-output, czy single output, different cases. Linear, as I explained, the model is linear. It means the input is linear combination of the output. The output is, the output is linear combination of the input. Okay, now it's correct. The model, of course, can be linear only with respect to parameters. For example, this model at the bottom of this slide is linear with respect to parameters. With respect to input values u, it is non-linear because we see here u square. But from such point of view that this model is linear for parameters, it is correct because it is A1, A2, and A3. So there is such form, general form. This form will be useful for identification procedures later on. And non-linear, of course, the parameters can be non-linear, dependency can be non-linear. Oh, okay. We will not deal with these such systems. Static dynamic I have described already to you. So we will deal generally with static systems. But at the end of this lecture, I will try to show you that for dynamical systems, we will do the same procedures as for static systems, but we must exchange the mathematical attempt. After some manipulation, I will show that we do almost the same, but the mathematics used in this model will be different as linear algebra in traditional way. Okay. You can. I will send you. Then you can write this description text. One element, two element. Okay, it is obvious. So we are now starting with model description, and as I said, we from here we will start only with description in the sense of system theory. I mean, U input values, Y output values. When necessary, it would be necessary, I will add eventually Z values, which will be denoted, which will denote noises or disturbance value, but rather without this value we will work. And as I said before, we can present our model in the form of certain mathematical formula, linear algebra formula, as you can see here. But sometimes it is necessary, it is useful to present our model in the form of block diagram. In this block diagram, we will use certain graphical symbols as gain element, in which this signal is amplified alpha times, and we obtain this signal. We need also so-called summing junction, in which we will sum the values of certain signals. And when we let's say model some real situation, and after modeling we will need to sum certain signals. For sure, if the modeling process is correct, we will sum the values of the same type. I mean, if we model correctly our system, we will not add to signal which interpret voltage to the signal which interpret current. Understand? If something like this happens, it means that we have made mistakes during modeling procedure. And moreover, this kind of divider will be also proper for a real system. It means that if we try to model electric systems, we will not go to such situation in which this V value will be current, because for sure, you know, for current we have real dividation, not like this when all values are the same. it is typical for voltage, not for current. For current, the current will be divided into some parts depending on the resistors of these lines. The voltage, no. The voltage is the same. So, and I would like to stress once again, if we proper derive our model from real description and then change the value into input and output, we will not find ourselves in such situation in which this value will be denote current. You understand? Or not?
Yes.
Yes, okay, so. Po polsku krótko, jak będzie dobrze zamodulujemy, to nigdy nie każe nam dzielić prądu w taki sposób, że się dzieli i się nie dzieli, bo musi się dzielić. Okay, sorry. And we need also crossing signal of signal, but during exercises we put here big point, and if these arrows will cross with each other without this big point, it means that they are lying like wires on each other. It means that not real connection, but just lying one on each other. This one, we don't. Okay. So now we can build such system. For example, you can observe this is not my picture. It is taken from presentation, old presentation, and it is not of my origin. Why? Because for me here should be here next arrow, ending of the arrow. Here also should be ending of the arrow, as I stress during exercises. Here must be arrows everywhere. Why? Because the arrow shows us the direction of the flow of signal. And we can say, of course, there is no problem because the signal from left side are going to the right side. Okay. No. In a moment, we will deal with so-called feedback connection, in which the signal which will be taken from the output and will go to the input back. So we need to show the direction of the signal, because the signal can be going from left side to the right side and in the opposite way. So when we see such system, it is inside of certain block formula, and we should find the model of in analytical way in the form of matrix description. Of course, we can say and calculate that y1 is equal. u1 is multiplied by 3, so here we observe 3 multiplied by u1 plus, okay. u2 is multiplied by 4, so here we can see 4 multiplied by u2, also with plus. Here, for the y2, we can see that signal u1 is multiplied by 2, but it's taken with minus. It means we substitute this signal in this summing junction from these signals. So as a result, we can see these two equations, and moreover we can build one matrix equation in such form. So this description has 2 rows and 3 columns. It means we have 2 output because we have 2 rows, and we have 3 inputs. Oh, here we have 3 inputs because we have 3 columns. Parameters are, as you can see. Okay. And now general remarks. The model can be built in different ways. The best model are obtained from derivation this model from the set of initial precise equation, as we did with this electric model. It means we had to our disposal Kirchhoff law. We describe with respect to this law every part of our system. Then we collect the system of equations. These equations were very precisely, let's say in 100% what we calculate and what we observe is the same. Let's say in 100%. So this model is certain. And having as an initial step the set of formulas, we think what is the goal of the system, which values should be input values and which values should be output values. And now we try eliminate different values which are in the system of initial equations in order to obtain this particular relation. And in this attempt is 100% good, because in this attempt we do not need any simplification, any approximation. It is rather problem of manipulation of equation to obtain solution, eliminate variables, and so on and so on. And these models are very good, because, as I said, they explain in 100% what is going on, because we can calculate using this model, and we can measure in a real system certain values, and after comparison we see that the result is 100% the same. So, but no, it's pity. It's not. The world is not so easy. The word is rather complicated. It means that when we try to describe some part of it, so-called system, we need to make simplification, approximation, in order to obtain a model. As second attempt is voltage divider, and okay, moment, tutaj sobie zrobimy. It is a remark from me. Moment. Okay. And once again. Okay. About this voltage divider and simplification which are needed to model its behavior, I will describe, I will show you on the next lecture because it's time to finish. We have only 2 minutes more. So maybe any questions or comments or something. Okay, a moment. I take this list once again. Okay, if not, so I thank you for attention and have a nice day and see you on the exercise on and this. So goodbye. See you.
Goodbye.
Thank you. Goodbye.
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 Thank you. Goodbye.
Thank you. Bye.